Okay, ladies and gentlemen, welcome to the second talk of this afternoon session. The speaker is Xu Yang, who is a professor at the Department of Mathematics at the University of California, Santa Barbara, where he has worked since 2012. He is an expert in modeling and simulation of multi-scale and interface problems and physical and biological problems, and is going to talk about asymptotic analysis connecting quantum and macroscopic scales in physics, their applications, and how to use AI to assist these complicated multi-scale derivations for the next hour. Please join me in welcoming Xu Yang.
All right, thank you, Axel. Thank you for the nice introduction, and thank you for the organizers for getting me here. It's very nice, and I'm very happy to see some of my old friends here, and also to meet some new friends here. Okay, so basically, the first slide I want to say is, in the late 90s or early century, the multi is a very frequent appearing keyword in all kinds of places. You have the multi-scale, multi-level, multi-grade, multimedia, multi-values, multiple multis, right? You have a lot of multis, right? And also in the grant program officers, they like kind of this word. For example, I know there's NSF once founded a proposal like, you have this something multi-scale, multi-value, and for multimedia, right? So, but don't get me wrong, I'm not simply saying the panel is doing a simpler job, like say, how many multis you have in the proposal, like you have 100, I have 200, so I win. It's not like this. I just want to mention that, during that period, multi-scale problem is kind of important, and it's kind of hot topic people want to study and see how it's investigated. Okay, so now it's time different, right? So everybody started talking about learning, right? So all kinds of learning skills, like reinforcement learning, machine learning, neural network, etc. Right? So in this talk, I want to share my sort of the experience, starting with a person trained on the numerical PDE, with working on multi-scale problems, from quantum to kinetic, from kinetic to diffusion, which is the continuum level, and then right now, how can this kind of things sort of connected to the AI assisted, which is you will see how AI can assist us when you're still working on the multi-scale problem. Okay, so before we touch anything about AI, I want to say something about what I have been done on the multi-area. Okay, so one of the important tools in multi-scale problem is asymptotic analysis. You have various versions of asymptotic analysis, depending on the perturbation theory, singular perturbation, WKB expansion, we're going to transform, then Planck, Nussen numbers, Mach numbers, and all kinds of limits. As long as you have some small scales, you can always say, right, so let's do a series of ansatz, try in, do expansion, only focus on the leading order, and if it's that's not enough, let's go to the next order, right? That's the standard technique, right? Okay, but it does give us something, right? So what basically it can give us is finding the connections between different level of physics, right? So you can go quantum to kinetic. So kinetic theory, kinetic theory is kind of theory that working on particle dynamics, or if you do ensemble of all the particles using density distribution function, and then can derive a PDE for this density, probability density function, and usually in the Boltzmann equation, Vlasov equation, Liouville equation, etc. Right? Okay, so it's kind of like a particle physics related to the statistical mechanics, right? And quantum is quantum mechanics, with the Schrödinger equation as the building block, right? So everybody starting working on something from the Schrödinger equation. Okay, and then fluid is something we are very familiar, like like a gas dynamics, right? Fluid dynamics, like ocean dynamics. When we listen or watch the weather report, this is based on the simulation of Navier-Stokes equation, which try to predict whether we have rain or not, what's the temperature look like, etc. Okay. All right, and the main challenge is if you ever if you went to Professor Shijin's talk yesterday, he mentioned the Hilbert 6 problem, right? You can justify the limits rigorously, and if that's successful, and then you can try to provide, right, a passage from different levels of physics. Okay. However, this is not that easy. Usually, when you take the limit, you have the layers, different layers, and also you have the scaling coupling together, which creates some difficulties. Okay, so then let's first talk about the connections between kinetic and fluid models. Right? Kinetic for fluid models mainly from mathematical side is how you start from like the Boltzmann equation or some simplified Boltzmann equation like a linear transport or even a Liouville equation, etc. How do you derive under some certain asymptotic to Euler equation, Navier-Stokes equation, diffusion equation, which are only equations about variables living in time and space. And kinetic theory, when you use the mathematical functions to describe the PDF, probability density function, and those functions are functions of time, space, and momentum. So, you lose the degree of freedom on the momentum, and you only see the observables, kind of like an ensemble of the order particles traveling in different directions. Okay, so how do you make this connection? There are very common tools. Hilbert expansion, Chapman-Asymptotic expansion, moment closure, BBU-GQY hierarchy. Well, the only purpose those technique methods are trying to do is try to eliminate the dependence of the functions on the momentum. So once you eliminate them, and now you have the functions only depending on time and space, and those are the continuum dynamics. Okay, and then there's no free lunch. You cannot simply say, all right, so all the functions are like mu free, like the momentum free. So it doesn't depend on freedom, and we do whatever we want. We have to say, it really depends on whether the system is on equilibrium or not. So if it's around equilibrium, say it's around the max gradient, right? So it's a standard and typical distribution of particles in statistical mechanics. And if the distribution is now too far away from max gradient, you can do the macro-micro decomposition and say, derive like the asymptotic scheme. Okay, and also when you have interface of boundaries, then the asymptotic is related to the singular perturbation theory, right? So like the typical problem that we have done near the boundary, if the inner solution does not meet the boundary condition, it has to create a boundary layer so that it satisfies the boundary condition. It's like once you have the vacuum equation, some fluid going to the left, but if you put a little bit of diffusion, make it with the second order PDE, then you have to give a left boundary condition. So the fluid going to the left hit the wall and then goes up, and it goes up quickly, and this is a boundary layer. Okay? All right. Okay, so let me try to give a simple example that I worked on many years ago when I was a PhD student, or actually when I was an undergraduate student. So this is a simple linear transport equation. But this equation F does depend on time, space, and momentum. It's linear, and this term is trying to mimic the quadratic interaction of the Boltzmann equation, but it's not in the bi-collision way. It's only describe the interaction between a particle distribution with the mean, which is the average. So the mu here, this is the one-dimensional model. This is one-dimensional model, and it's not really one-dimensional because in a one-dimensional setup, the particle can only move to the left and the right. And this one-dimensional problem is like a simplification of a 3D radial Hill transfer equation with the radial symmetry. So in the 3D setup, the distribution in the radial symmetry will also depends on the angle. And that angle is described by the mu. So mu is the cosine theta. Theta is the angle. So the range of mu is from -1 to 1. Okay, and then what I try to study during my student time is say how can we derive a diffusion limit for this linear transform equation. However, when the sigma has like a discontinuity, like say in the 1D problem, you have the left domain, you have the right domain. Then for the left one, sigma may be equal to 1. For the right, you have sigma equal to 100. So you have a big difference between these two sigmas. How do you derive the diffusion limit? And when you derive the diffusion limit, how do you handle the interface layer problem? Okay. So how do you do the asymptotic? This derivation is you first write down the standard asymptotic analysis perturbation theory. You say, okay, so actually I skip the discussion here. In standard perturbation to say f is equal to f0 plus epsilon f1. But when you plug in, you will see the dependence on f0 only depends on t and x. It does not depend on the velocity. Okay, and then you plug in this ansatz into the previous linear transfer equation, and then you will see the equation of the leading order satisfy this diffusion equation. However, for the interface layer, this is only valid when you have enough regularity. But when the sigma does not have enough regularity, you're going to have the, as I described roughly before, you're going to have an interface layer across the discontinuity of the sigma. It's like when you learn the numerical scheme for say conservation law, you have shock formation, and when you simulate the propagation of the shock, unless you are using very delicate shock capturing scheme, the numerical results you see will see a layer sharply transition from the lower part to the upper part, satisfy the Rankine-Hugoniot condition. Okay, and then the direct simulation will say you have to really use the small mesh scale in order to resolve the sharp transition boundary layer or interface layer. And the numerical schemes we propose there is the so-called domain decomposition method. To use the domain decomposition method, the idea is to say it's kind of like a Schwarz iteration, but when you do the Schwarz iteration, you have to derive the connecting interface conditions, connecting the solution of the left to the solution of the right. And that is derived by the Chandrasekhar H function. And we use the Snell's law. So the Snell's law is describe the behavior of the particle when it hits the interface. It's like the light, right? When you have the light hitting the interface, you have some light reflected, you have some light transmitted, and it satisfies Snell's law. And this is a numerical simulation, and this part, the enlarged part is the right figure, is to show you a sharp transition boundary layer. So away from those interface layers, it behaves the same as the diffusion, but near the close to the interface, it does have the layer. Okay, and later on, I keep working on this direction for different, more complicated setup. Particularly, we did the spin transfer magnetization dynamics. This is about the spin transfer talk. We start with the Landau-Lifshitz-Gilbert system coupled with the Vlasov system, and we take the moment closure and we derive the diffusion model for spin. Okay, so the Vlasov system coupled with the Landau-Lifshitz-Gilbert, the Vlasov is for the spin dynamics, and the Landau-Lifshitz-Gilbert is for magnetization. So it's a spin-coupled magnetization. And when you do similar things on the spin dynamics, you can derive a diffusion model for the spin dynamics coupled with Landau-Lifshitz-Gilbert. And we also have a different version of domain decomposition for two-scale transform it depends on depends on the materials from the left and the right. We have different interface conditions connecting the decomposed domains, and connecting to learning, trying to connecting learning. We proved recently some multi-scale pin analysis on the convergence of pin when you simulate the Boltzmann equation with different scales. The proof for this pin analysis, first, it has the key components is you have to control the generalization error and you have control the total error. Usually, it takes a lot of time to prove the convergence of the generalization error. Our results rely on the smoothness of the activation function. We have to assume that the activation function is a tanh, which is a very smooth function. And in that sense, we are able to get from the previous literature results that we can approximate any functions as long as our neural network is large enough. Okay, and then based on that results, we are able to control the generalization error, and then with the generalization error being controlled, it's easy to get control of the total error. Okay, so that part is about how you go from kinetic to fluid, and then second part is how do you go from quantum mechanics to kinetic. So quantum equation, this is like a one-body Schrödinger equation that we have seen a lot, right? It's a very simple equation. It's a linear, and this operator is Hessian, so it conserves a lot of things. So it's a very nice equation. And for this one, if you consider this Schrödinger equation in the semi-classical regime, so the semi-classical regime is it's an interesting word, right? So it's not a classical, it's not quantum. It's to say when you rescale all the parameters in the standard Schrödinger equation with like the Planck constant, electron density, electron charge, and all the parameters you put together and you say, all right, so now I have a small parameter, and this equation is non-dimensionalized. So it's no dimensionality. And in this case, the epsilon is sort of related to the ratio of the size of the typical scale of the electron dynamics compared to the domain size. So heuristically, when you say the epsilon small, it's not due to the Planck number is small, because if you consider the atomic units, Planck constant will be simply 1, right? So in general, it really depends on the metric we try to measure this. And usually when epsilon is small, it's referred to the domain size is large, and makes the system more look like a classical system. Okay, and to connect or to see some kinetic dynamics starting from the Schrödinger equation, there are many existing tools. You can take the Wegener transform, which you consider the density function of this wave function, the density matrix of this wave function, and you derive the equation for the Wegener function, and that's usually you get the Wegener equation. And if you are considering some truncations when epsilon is small, you can get a Liouville equation or some correction terms on the Liouville equation. And another way, which I have been working a lot along this line, is to directly using the WKB expansion related to the geometric optics, which is a very straightforward way that you can see Newtonian dynamics from this Schrödinger equation. And this WKB or geometric optics has difficulties when those rays are forming a Cauchy, means related to the classic fluid dynamics is when you have Berger's equation, no matter how smooth your initial condition is, under some certain conditions, you may have a form, you may have a shock formation, and when the shock formed, the weak solution becomes to be not unique, and right. So one of the weak solution is given by the viscosity solution, and the viscosity solution is unique. But you can also have the multi-value solution, right? And when you have the multi-value solution, you have different types, right? So how do we take care of the asymptotic expansion once we have the toxic form? We can consider the Gaussian. Instead of the rays, we can consider Gaussian or Stacey asymptotic expansions. This has a lot of family of numerical or asymptotic expansions, like a Gaussian wave packets, essentially related to the dynamics of coherent states dynamics, or Gaussian beam methods, which is you do the beam summation and you try to get a asymptotic expansion about that. Or this is some work I have done, like the frozen Gaussian approximation. All this work is about one body picture, and of course, the asymptotic not only exists in the one body picture, it also exists in many body pictures. Right? The well-known asymptotic expansion for many body picture is the Born-Hammer approximation. The small parameter there is not the size ratio. The small parameter there in the Born-Hammer approximation is the ratio between the mass of the electron and its nuclei. Right? It's like 1/1000 or something. And then once you separate the dynamics of the nuclear motion and the electron dynamics, for electron dynamics, it's still hard to solve because the dimensionality of the electron dynamics is like 3n. N is the number of the electrons. So it's very high dimensional. How to solve this? People use the density functional theory, and it's not the only way. You can also do the quantum Monte Carlo, but one of the popular methods people use is density functional theory. And this theory is to say we try to do the dimension reduction. Instead, we solve one 3n dimensional Schrödinger equation. We try to solve n 3-dimensional Schrödinger equation. Right? So the dimensionality becomes to be 3, and the number of the equations become to be n. And this seems to be a lot of gain, but there are a lot of ambiguities during this reduction, mainly on the exchange correlation function. Okay. All right. So in the next slides, I'm going to focus on this part, and this part, which are those works I have done quite a lot. And try to get some numerical results or asymptotic expansions starting from the one-body Schrödinger equation. Okay. So what is the WKB ansatz? So the WKB ansatz, some of you might have also seen this. It's kind of it's like the Madelung transform. Although the Madelung transform does not have this small parameter there, we assume the ansatz, and the purpose is to do amplitude phase separation. We try to use this ansatz and derive asymptotic expansions for S and A. So and once we derive the equations for S and A, and then we can, by not directly solving the equation for psi, but by solving the equation for S and A, we are able to reconstruct an approximation of the dynamics for the wave function. Or if you are only care about the observables of this electron dynamics, say if you only care about the probability density, you may not need to solve S perfectly, because when you take the absolute value, this term is gone. You have to solve S because when you solve A, it's related to S. But what's the benefit of doing the WKB ansatz? There are many benefits doing this. First, you can see some dynamics like the classical Newtonian dynamics from this expansion, especially from the Ackno equation. And the second is you save the computational, you have some computational efficiency. Why? It's because if you look at this equation, and if you try to solve this equation directly, you look at the wave function. Because the existence of this small parameter, the solution behaves very oscillatory. So why it's very oscillatory? So if you forget about this term for the moment, and then this is the ODE. the solution of this ODE will be simply psi equal to an initial condition times e to the vi over epsilon. And this I, v over I epsilon. So this I makes this e to the whatever to be like a phase function. So by Euler formula, you have e to the I whatever, I theta equal to cosine theta per I sine theta, right? And this theta is related or proportional to the potential divided by epsilon. So say when epsilon is small, like 0.01, then this exponential I times v over 0.01 will be like a cosine 100 Vx plus I sine 100 Vx, right? And then the cosine 100 Vx will be a highly oscillatory function, right? Okay, so directly solving this, if you have a nice boundary condition, it's okay, because you say if you have periodic boundary condition, or if you have a decay boundary condition, you can apply a spectral method. And if you don't have that kind of boundary condition, say you have to use finite difference or finite volume methods, then you need to resolve that small oscillation in order to get an accurate solution. And when you get the asymptotic equations for S and A, S satisfies the Ackman equation, A satisfies the transport equation. So those equations are epsilon free. Those are the large scale equations. So it's macroscopic, and you can use standard numerical methods to solve those macroscopic equations very easily and get efficiency. However, so if you look at this Ackman equation, and if you take the gradient of this Ackman equation, it becomes to be a forced Burger's equation. And as we all know from our knowledge on fluid dynamics, when you have a forced Burger equation, no matter how smooth your initial condition is, it can develop the causes, right? Develop the shocks or reflection or something else, depending on the initial condition. Okay, and when you have the shock formation, that means the solution becomes to be singular. And in this case, in the optics sense, this is called caustics. So the caustics is at the very first day when I started working on this, my advisor called me to his office and pointed out some picture like this on his door and to say, right, look, this is caustics. It looks a lot of things going together and forms a lot of high densities near here. Okay, and then I have to study, right? So where this picture comes from and why all the characteristics going together to here, right? And this is due to the characteristic line of when you solve this Ackman equation. So when you solve this Ackman equation, we can solve it by the method of characteristic lines. So we differentiate, and then we can define the dx over dt to be the velocity, and we do the dq over dt equal to the velocity, and then you derive the dp. So p is equal to gradient s. The gradient of phase gives you the velocity, and if you take the gradient of phase, this is u plus u dot ux plus u grad v equals 0. And then this is, say, you do the standard method of characteristics. You can say dx over dt equals v, and then dv dt equals the negative gradient potential. So it's a standard Hamiltonian system. All right, and when you do the standard Hamiltonian system, and some initial conditions of the potential will make those characteristic lines going together, and especially those lines which is envelope that has many characteristics going there. And if you look at this solution, you will see the amplitude A will become to be infinity. Mathematically, it relies a little bit derivation on the conservation law. You will see a squared times some function gradient s, if I remember correctly, is conserved. And then when the not gradient s, you will see a squared times the cross section of the ray tube is conserved along this ray. And then when you have caustics, the ray tube, the cross section of the ray tube shrink to 0. And then the only way to make this quantity still conserved is you have to make A blow up. Okay. All right, so then how do we handle this? I mean, when you have some blow up, you definitely have a fail of this ansatz. Right? I mean, when you do the asymptotic derivation, if you don't care about the accuracy, you can do whatever you want. Like when you do the quantum field theory, I mean, even though the series does not converge, you can still try to at least write down equation for the leading order, right? Okay, but mathematically, if you want to justify the accuracy, you have to keep the higher order terms. You have to say, all right, so this is the A0 plus epsilon the phase, and then plus A1 times another phase times the epsilon, and then plus epsilon squared A2 plus dot dot dot, like what we have shown for the expansion of F in terms of epsilon. We try to derive the diffusion equations. Okay. And then you will see when A blows up, the next order correction also blows up, and then the next order correction also blows up. That means the remainder error blows up. So that is not accurate. So how do we handle this? This is called Gaussian beam or frozen Gaussian approximation. The idea is actually quite nice. The idea is to say, right, so the reason that intuitively this amplitude blows up here is you have infinitely many rays, which are the characteristics going exactly to the same points at some point. Okay? And that blows up the amplitude. However, if we are able to make those particles, those rays, having some volume, right? So it's like a Gaussian function. It's a Gaussian function around the rays, centered around the rays. And then we may able to, right, make those infinite coming together to be a finite collection of the Gaussian function. Because, the particle does not have volume, so a place can hold as many particles as possible. But if you have a Gaussian function, it has occupation, and then this space is no longer hold infinite many Gaussian functions. It has to be a finite Gaussian functions. And these finite Gaussian functions may give you a way to get over the singularity formed on the amplitude when you have the causes. Okay, so how does that happen? It happens, naturally by a Taylor expansion. We try to look for a asymptotic solution not only on the method of characteristics given by the set of ODEs. We try to find an ansatz solution around this method, around this characteristic line by Taylor expansion. So we Taylor expand. So this little q is the center of the Gaussian function, right? So I mean, assuming the Hessian function m is positive definite, and then the little q is the center of Gaussian. In one-dimensional case, this is a half m x minus q squared. So this ansatz has an extra degree of freedom of the center. So, okay, and this center, this p and q are satisfying exactly the same of the characteristics. So p and q satisfy the Hamiltonian dynamics, which is the geometry rays. And this ansatz means we are trying to derive the asymptotic about the Gaussian wave package dynamics centered around the characteristic line. And this introduces a little bit more degree freedom, especially we are going to having a function of the Hessian function. And this Hessian function, if we naively doing the Taylor expansion, it actually does not help because compared to the standard ray dynamics, the Taylor expansion only introduced the Taylor expansion error, but nothing else. And the key part is, in order to make this guy work, you have to make this guy to be a Gaussian wave package, in the sense that you make this Hessian function originally from Taylor expansion as the real value function, now to be a complex value symmetric matrix. We will make m to be complex, and then the imaginary part combined with this I will make that kind of like a decay. So this will not be like a global solution. It's a local solution around the rays. And then the following will be a mathematical proof. So how this can work is, before we have the conservation law says, the a squared times the cross section of the ray tube is conserved. And when the ray tube shrinks to a 0, then the ansatz dies, right? And now we have to show that this m, if originally is well behaved, means the imaginary part of m is positive definite, then this imaginary part of M has to stay positive definite for all the time. And if that's true, then this ansatz will be always valid for all time. And then how do we show that? We have to do a asymptotic analysis. We plug in, then we derive the equation for S, we derive the equation for Q, and then we derive the equation for M. Okay, and then the equation you write down is the matrix Riccati equation. You can decompose this as a linear system. M is equal to a ratio about two matrices, and these two matrices, by some certain constructions, you can show that. Say if M is equal to P over Q, and then you show that the Q is always invertible in the sense, right? Q is always invertible, so M is always non-singular, and then it makes the beam decays from the center, and the linear superposition of this ansatz makes even though you have caustics, you can still have a valid solution. Okay, so this is one of the simulations of what I did for Gaussian beam method. We have a pretty small epsilon. It's 1 over 4,000. And we have the caustics forming here. And then with the formation of the caustic, we are still able to, this is, although this looks big, but the scale is 10 to the minus 3. And this scale is 0.2. So it's related to the scale of the epsilon. Right? And then they match very well. Okay, any questions? Okay, and then the problem about this Gaussian beam method has a drawback, which is it's not afraid of when M becomes to be when the Gaussian becomes to be very narrow. Say when you have a lot of beams going to the caustic, and then naturally the beam will become narrower and narrower. But since we have proved a theorem says M never becomes singular, so this beam never shrinks to a point. That's why even though you have caustic, we are still able to construct a valid asymptotic solution. However, when the beam is not going to a caustic, it's going to some place like the rediverge area, and then naturally, in order to still maintain this is a valid asymptotic solution, this Gaussian will become very, very wider. Because when the ray diverge, everybody is going out. If you still want to occupy those kind of solution space, the Gaussian has to be wide. Otherwise, we know this is no longer a solution. Okay, and then when the Gaussian function becomes wide, the problem comes from the Taylor expansion error. So we did a Taylor expansion truncation. We only keep the quadratic terms. We ignore there are I have to say there are high order Gaussian beam methods which keeps the high order expansions, but that's another story. But just for the standard setup, classical Gaussian beam methods, we truncate at the second order. We throw out the triple, quadruple things, and those things, when the beam becomes very wide, that means x minus q is large, and those terms become large, and the errors caused by the truncation of those terms will pollute the accuracy of the Gaussian beam. That's called the beam spreading issue. So Gaussian beam never have a problem when the beams are becoming narrow and narrow, but it has a problem when beam spreads. So how do we fix this the beam spreading issue? Of course, you can do the Euler Gaussian beam methods or semi-Euler just for efficiency, and also you have various versions of Gaussian beam methods for different types of Schrödinger solutions. So the standard Schrödinger equation is one body, but you can also say the Schrödinger equation on the lattice. The lattice Schrödinger equation means the potential is not a function of x, but a function of x over epsilon. So the scale of the lattice of the background is the same as the scale of the electron dynamics scale. Okay, and then in that sense, you no longer can do the double KB expansion, but you have to go by the block decomposition. So you use the block functions of the eigenfunctions of the Hamiltonian operator, and they are orthogonal. You do the orthogonal expansion, you plug in, and you derive the coefficient dynamics. But it's based on the same thing. Okay. And we have done a lot of work on Gaussian beam methods, Lagrangian, Eulerian, different potential things, and then Xu Jin had a review paper on acta numerica, which I think at least half of the total pages are about those papers. Okay, so as I mentioned, Gaussian beam methods has a drawback, which is the accuracy will be polluted when you have the beam spreading issue. And naturally, we would think the so-called frozen Gaussian approximation. The frozen Gaussian approximation is to say, we're going to simply take away the dependence of the Hessian function. So we're going to only consider the coherent states. Okay, so we're going to fix the weights of the Gaussian. So we've frozen it. So we no longer have the dynamics of the Hessian matrix, and then that means you no longer have the spreading issue because it never spread. It never gets narrow. It never gets spread. So it seems very nice. However, the drawback of doing so, maybe I can show you. Let me see if I have. I'm not sure if I have time to show something. But I will try to show something. So basically, you start from the standard Schrödinger equation. Maybe I ignore the potential for the current moment. And then when you do the Gaussian beam method, you say, all right, so mine is like let me do the one-dimensional problem just to be simple. Okay, so when you do this, you plug in this part in here. Of course, the first order is the order one, right? Because you can see when you take the time derivative, the high order of this ansatz goes to the time derivative has to go here. Because when you take the derivative of time on the exponential by chain rule, this is exponential the whole thing, and then you take the I over epsilon out, right? So when you take the time derivative, the high order of this part goes here. And then this is order one because you have the I epsilon here. And then the epsilon squared grad is the same thing, right? So you have to make the Laplacian acting on the phase twice in order to have that. So that means the first order is order one. And then for the first order order one, you have the acting equation. And then for the next order, you're going to have an equation for A. I probably don't have time to go over the details, but I need to remember the equations. But I want to say that the problem is when you go to the next order, you have an equation for M, right? So this gives you the equation for M, which is the Riccati equation. So this is the Riccati equation. So the problem is the Riccati equation does not have a constant solution. When you have a non-zero initial condition. So this does not have a constant solution. have non-zero equation. Right. So if you have a constant solution to the Riccati equation, then it has to be m to the 0. This is special case because I assume the potential is 0. So that means, right, if I simply propose another ansatz by fixing this, to be a constant, from the mathematical point of view, I take away the degree of freedom of this ansatz. It no longer have a function depending on t and y. For another, you will see at this level, this equation is no longer true. So that means, this single ansatz, if I just simply make it to be frozen, it will be no longer a valid asymptotic expansion of the solution to the Schrödinger equation, right? Then how should we make it work? What's the magic? The magic is, usually people call it beam cancellation or something. Okay, beam cancellation. Okay, so for beam cancellation, what happens is the beam cancellation happens in the weak sense. So we cannot have a valid asymptotic expansion by just using this ansatz. We have to use asymptotic expansion by using many linear superposition of this frozen Gaussian ansatz. Say the ansatz now is no longer a simple algebra function, but it's an integration over the phase space. And then by doing this integration of this phase space, the magic happens by this lemma. So this means equivalence. This equivalence means they are equal to each other in the sense of this integration. And when you have, so I have a couple of slides for how to show this is true. When you have this kind of integration, you get some elimination of dependence on the x minus q. Amazingly, or some surprisingly, you can see when you have 1 x minus q, this order is the order of epsilon. And when you have 2 x minus q, this is still the order of epsilon. And then when you have the, b times x minus q to the power 3, you have the order of epsilon squared. When you have the power of x minus q to the power 4, you still have the order of epsilon squared. So essentially, that means, when you have the odd power of x minus q, it's kind of, scale up to the next order of epsilon. And when you have an even order of x minus q, it's equivalent to the same size of x minus q. What do I mean by x minus q size? This is related to the decay property of the Gaussian function. So decay property of a Gaussian function. So think about this x minus q guys here, right? So x minus q squared. So suppose this is a constant. Let's say this is just a 1. And then, they cannot be. This is a complex value. So let's say it's 1 plus I. Okay? And then if m is equal to 1 plus I, all right? And then you can see this is something times e to the negative half x minus q squared times epsilon, right? This is something with complex phase. And then if you look at only on the decay part, so this will be have profile centers around Q, right? And then this is not a compact function, but it's like an almost compact function. And almost compact function makes this x minus q is at the order of square root of epsilon, because the standard deviation of this Gaussian function is square root of epsilon, right? And then you have the 3 sigma on the left, you have 3 sigma on the right. So this is like a 6 sigma range, which is a square root of epsilon. And then surprisingly, what you can see from this asymptotic expansion is this part, you should have the x minus q at the order of the square root of epsilon, but it goes up to epsilon. And this part, you have 2 of them, and square root of epsilon times square root of epsilon gives you epsilon. It's perfect. So that means there must be some cancellation when you try to do the equivalence in the integral sense. And this cancellation, the magic happens. You have this integration by parts. So this is the total phase of the ansatz once you do the integration on the phase variable p and q. And we can show, take the derivative, make a construction, and then we can connect this x minus q with some matrix connecting to the derivative of the phase. And when you connect it to the derivative of the phase, right, so the x minus q, you can simply replace it by the partial z of the phase, and then you can do the integration by parts. When you do the integration by parts, it goes the epsilon instead of square root of epsilon. And that's the magic that, when you fix the ways of the Gaussian function, you are still able to derive the valid asymptotic expansion. It's because the actual degree of freedom is gets eliminated by the so-called cancellation, which is the integration by parts. And once you have the integration by parts, you're going to have the the derivatives about the z. So what is z? Z is the partial q minus I partial p. So it's the partial derivative defined on the phase plane. Okay, and then with this partial integration, we no longer like by algebra calculations we are able to derive the asymptotic equations, because every time you have the x minus q, you have to do the integral by parts, right? Integral by parts gives you makes the asymptotic very complicated compared to the direct plug-in. Okay, and then some results. I skip some algebras, and then by a lot of tedious calculations, we are able to show that the amplitude equation for the standard one-body Schrödinger equation is given by a neat formula, and we are able to show that you can still have the valid solution, when you have causes. Okay, so let me go a bit quick. This is something still FGA, but the FGA actually the motivation of this part is I want to say that the FGA, when you have complicated equations, the FGA can be very complicated because you have the integral parts and because you have the fractional derivative from the the fractional Schrödinger equation, and it makes a asymptotic derivation very complicated, and even more. If you're working on the system, say elastic wave system, you can still do the FGA approximation. And you have the decomposition into the P wave, you have the decomposition into the S wave. For S wave, we have the SH and SV, right? And SH, SV has the phase, you have the phase degree of freedom, right? And then it makes the derivation very complicated. So probably only have 2 minutes, and then this is for Dirac equation, and I just want to show you we did the dirty work, and we carried the numerics, and they can match very well. What I want to say is basically how, what I'm trying to do. I mean, I have not done a lot of work on this. I only worked for a few months. And I want to use this example, say, to show that what I want to try to do. Right? So when you derive the equations for the phase, when you derive the equations for the P and Q, and for A is the most complicated one. I mean, I don't even remember that, although I have been working on that for many times. You can easily make mistakes. And how about we use like a large language model? Say, your first question to ask, what is the Schrödinger equation? Can you give me the equation for amplitude? Can you give me the equation for the Ackman equation? Oh, sure. I have tried that. It can give you a very correct answer. Say S satisfies the Ackman equation, A satisfies the transfer equation. It's perfect. Oh, now you try to ask, can you derive the frozen Gaussian approximation for me? And then they started doing sort of like the Gaussian Biot method, and then they fixed this M. And then, of course, you plug in, I don't know whether it plug in or not, but it trained in a system of equations that you have Ackman equation perfect. You have the amplitude equation perfect. And then after here, because, you tell it to say this is frozen Gaussian approximation, so it will not use any, variable dependent Hessian function. And then they got us stuck here. And then he started doing something bullshit, like, I don't care whether it goes, this is something I get. Okay, so this is what a large language model can do. But what we are trying to do is, if you are expert, of course it's doing something nonsense. That if it's not, you are not an expert, how much you can trust it that give you a delivery, right? So that's, and we try to do the so-called automatic derivation with the AI assisted. So we, I mean, the general plan is we do a loop like this. We decompose, scratch, relax, and refine and learn. So this loop is to say, let me finish the plan. Right? The plan is, all right. So when I use a large language model, I say, all right, so I start with a certain equation. Can you do the frozen Gaussian approximation? And then they start doing a lot of things. And then I say, all right, so if you fix, right, so I only give a sketch. And this sketch, of course, it has lots of mistakes. So I make it to be host. And I make it to be host, and I use the human knowledge to adjust it to say, all right, so I'm going to say, if you froze this part, you have to work on the integral sense, right? So you fix the ansatz, and then it started again on scratch. So I want to assist the AI in a way that it can generate a reasonable sketch, like decompose the whole thing into a very, very small problem. And for each small problem, we can do a very quick search over like the collection of tactics, so that you can complete those little problems in a very quick way. Of course, this is very ideal because not every problem can be decomposed in that way. Then what we try to do is like an interactive way. Is if some problem that you cannot really fix by, let's say, you using lean, because lean is very very rigorous way, but it cannot do very complicated problem yet. So we just say, okay, let's assume this is true, and then later on we can fix it by like a human knowledge, and then in that sense we can really save a lot of searching time and generate an auto derivation. Not yet, for ideally for this asymptotic expansion. I think that's all I want to say. Thank you so much.
Okay, do we have any questions from the audience? Yes.
Okay, there are many approximation methods and they have fancy names, but in general, I think they are all just a Taylor expansion, and you add some leading terms or a few leading terms, and what you do is actually picking a physically known small parameter and expand the a function around it.
Yeah.
Is so. Is that right? Is my understanding right?
Yeah, that's true. So that's why I say asymptotic analysis is one of the useful tools in all the kind of multi-scale problem. The problem is, usually the very first step is kind of the most important, because what kind of ansatz you want to pick, right? It's the standard, the Hilbert expansion, or you do like the singular perturbation, or you do the WKB expansion, right? You have to have some intuition on what kind of ansatz you want to work with, and then you do the tedious work, right? Usually the harder part is first you have the reasonable ansatz so that it can give you some like physical, meaningful quantities, and those are related to the next level physics or something. And then the second step is usually happens in the derivation. The derivation can be very tedious and easy to make mistake, and that's the motivation that why I try to like large language model, etc. that can help us to fix those kind of things. Yeah.
Thank you.
Yeah.
Thank you for the talk. You mentioned dimension reduction methods. Have you worked on those?
Dimension reduction for the density functional theory.
And if yes, did you have problems with imposedness and how you handled this?
Bosons.
No, if you worked on dimension reduction, did you have problems with problem being ill-posed in how you handle that?
Oh, that's a good question. Yeah, that's a good question. Yeah, we do have the ill-posedness when you do the dimension reduction. And for the dimension reduction, I mentioned is particularly on the density functional theory for approximating n-body electron dynamics. In that sense, we have to make assumptions on the exchange correlation kernel, like the smoothness, etc., so that we can make the problem well posed.
I mean, if you choose kernel, you don't have ill-posedness at all?
Well, for example, how do you derive the exchange correlation kernel? And in general, only, Next. That's the Kongshan, right? I forgot the name, but they prove a theorem that there's a one-to-one response between the wave function and the correlation kernel, but nobody knows what the mapping is look like. So one way to do that is kind of the smoothness is to say, let's say this is like the uniform electron. And what happens in this case if you do the dimension reduction? And let's use that as approximation. So this kind of like smoothness is introduced by some assumptions on the distribution of the wave function. That's one way that I know people do in order to make it well.
I think we have time for one more question. One quick question. I guess I have a quick question about the icon equation. What boundary conditions do you have on?
Oh, that's a good question. So for icon equation, I can only give the boundary conditions. No, it's like the one-way wave equation. You can only give the boundary conditions on one side, okay. Not the side that the characteristics go into, but where it comes from.
I see. So how do you know that the viscosity solution is the right solution?
Oh, so the viscosity solution is only a right solution before the formation of caustics.
I see. Okay.
So after the formation of the caustics, we have to go to the multi-value solutions because you have to keep the linear superposition property about the waves, right? Okay. So no matter it's a Schrodinger or wave equation, it's a linear equation. That means when you have the characteristics cross each other, you cannot say let's take the average, only take the first arrival. Right. So if you do the viscosity solution, the solution you get is like a first arrival waves. Okay. So the later waves will be ignored. But that lose the linear superposition because they no longer are linear, right? Thanks.
Okay. Any further questions we'll discuss during the break or later with the speaker. So let's thank the speaker again.
Right. Thank you. Thank you, Axel.
And then we'll be back here at 2:30 for the last talk of this session.
Okay.